In my backpack, there are 7.
Oh.
And can you explain why we can do that? Why we can subtract?
Yeah. Let me build up to that point.
Okay. Because I was getting really confused.
Everything you just went around my head. It was which section?
Section number 10, page 697, or a number 25.
All right, guys, I have a question from section 10.7. Partial fractions. It's page 698. 25.
Do you want this? No. What? What? Harvey? Ew, who is that? So that's an irreducible denominator, right? No, that's a reducible denominator, which I did by synthetic division. Is there an easier way to reduce that denominator?
Yes.
Okay. Grouping.
Yes.
Oh, grouping. I love that one.
So, special place in my heart for those people that look at this problem and want to do synthetic right off the bat. But synthetic, while it's nice, it's not the nicest way to do something if there's an easier way. And the whole point here is partial fractions. I want to decompose this into its parts. So the very first thing I have to do is see what kind of parts I want to set up. So that's why I'm going to try to factor this. There's 4 terms, so of course, what method do I try?
Grouping.
Grouping? So that's step 1.
What did you think? I did synthetic division because I like to do things the hard way. Place in his heart. Yeah, it took me 4 hours to do this problem. That's like abuse. It was abuse.
So we group this thing at 2x squared. X squared. 2x minus 1 minus 4. And then you actually end up with x squared minus 4, which is x plus 2x minus 2.
Yeah. That's much easier.
Yeah.
So what you did is...
And the nice thing with this is if you think ahead, will you be able to apply my method to this?
Sure.
Which is where you choose values for x? Hell yeah. Right, in fact, you'll be able to do that all the way through and get it done. You don't have to do any matrix work at all. Yeah?
Or would you do it as like ax plus b and then like c and d over x plus 2 or x minus 2? Or would you do like cx plus c over...
All right, let's slow down a second. So my bottoms are definitely going to be what?
2x minus 2x minus 1, x plus 2, and x minus 2.
Tops have always got to be how related to the degrees of the bottom?
1 minus
1 degree less. What's 1 degree less than linear? Constant.
A.
Right? A, B, C. Nobody needs an AX plus D or anything like that because no bottoms are made up of things that are 2nd or 3rd or 4th degree.
Right.
So all the tops can be constants. Yeah.
like 2x squared minus 1.
So if you make a mistake and don't factor this all the way down, you'll actually get an answer that's correct to the point where it will, when you add them back together, you will get this, but you will not have decomposed it all the way. It's sort of like factoring 18 all the way and getting 9 times 2. Well, yeah, 9 times 2 is 18, but you didn't factor it all the way. You didn't break 9 down into 3 and 3. Does that make sense? I mean, that's the idea. So I want to break this all the way down. I got to be sure that I break the denominator all the way down. Cool. And I don't know, do we want to do this one, or is this almost too easy?
Let's do it.
I always love when I say that and I have somebody that's like, shut up. It's not easy. Alright, but allow this to be not that bad. You should all be able to factor. If you can't, I don't feel sorry for you. You will die in this problem, and you should. You should be able to factor by now. Yeah.
So on the right hand of the equation, it'll always have pluses in the middle. Is that because it means like and? Is that because like?
Well, the whole idea is this is coming from the addition of several. Now, A, B, or C, any of them could be negative.
Yeah.
So I don't have to worry about minuses. But it's because of the idea that, I mean, if I have something plus something else,
equals those
That's
together.
what I'm trying to work backwards. So this will be x, this will be 3x minus 4.
4, yeah.
So all I'm trying to do is do this process in reverse. So I'm saying I don't know what that is, and I don't know that is, but I know it's addition of all these pieces. Because these would need an LCD, and the LCD would obviously be this times this times this, which is what that is.
I see.
Cool.
I get it. Okay.
Maybe.
All right.
I got some deer in the headlight looks from some people. Like, did we do this? But how would I do the next step? Just to go a little further here.
So you.
Yeah, I'd multiply everybody by this LCD. So I get over here, I just get the top. And over here, I get A would pick up what?
X squared.
Basically, yeah. Plus B would pick up the other two things. And C would pick up these guys here.
The
It's pretty
LCD
cool.
would be the whole denominator.
So again,
The LCD would be the whole denominator.
exactly. So pretty cool with that step from here to here. So pretty cool with that. All right. Right, I said, if I make that sound, it'll stop asking. Oh, okay. And now, you could multiply this all out and equate coefficients, and that would lead to possibly matrix problems, at least systems of equation problems, right? Or you could attack this my way, which is just to pick values for x and eliminate stuff more directly. So, for example, if x were, what? 2. So if x were 2, I get 4 times 9, 36, minus 18 is 18, plus 6 is 24. If x is 2, this is gone, and this is still there. That would be 4 minus 1 is 3 times 4.
12C.
12. So then C would be
Right.
2.
2. I like it. And then you can just keep going. You can go if x is
-2.
-2, and then if x is 1/2.
Okay.
Finish it out like that.
Can we do it one more time?
Yeah, so if x were -2, who goes to 0?
Both
The A piece goes to 0 because that's going to be 0. The C piece goes to 0, and you end up with, on this side, you end up with -4 times -5 is 20. Check me out. Yeah, -4, -5, so that's 20b. On this side, if you plug -2 in, you get 36 plus 18 plus 6, 60. So B would be 3, and then 1 due to 1. So when my method, again, it really doesn't have a name. When the choosing values for x method works all the way, that kicks ass. When it only works halfway, it's kind of bad because people get a little freaked out. If I couldn't do it one more step, I'd have to plug in my value for C and B, figure this out, and pull it over here. And then I could just equate the rest of the coefficients. Yes, ma'am.
Will you be nice and put your way on the test?
I'll be putting this type of thing on there, yeah. So you can either use this method or you can use the equating coefficients method, either way. Yeah.
So if you were to do the equating coefficients method and work it all out, would it be acceptable to put everything into a matrix in a calculator and do it that way, or do you want us to do a whole matrix?
No, if you choose to go that way, you must show me the work.
All,
Yeah.
the whole matrix. Okay.
All right.
Just
I would
making sure.
highly recommend maybe not go that way.
I'm going to use Waller theory on the test.
Yeah.
So if you go to the last step and put the matrices in, or you have to do the matrices by hand.
Yes. If I give you, I'll tell you this. If I set up a problem where you get some tremendous ugly matrix, then I'll tell you it's okay to use your calculator. Because maybe there's a problem where my method doesn't work and you end up with it's tremendously ugly. Now, but what I'm saying is if I give you a problem where you don't have to do that to yourself, where if I'm kind of a smart student to the point where I realize if I just set up the matrices and he lets me put in the calculator, that's actually the easiest way to go because then I don't even have to do this. I don't like that. If there is a way to do it that's relatively easy by hand, and you choose to do it the harder way, you got to live with that decision all the way through. Yeah.
So for the homework, in order to receive credit, do you have to show each intermediate step between matrices? Because I didn't use my calculator, but I...
Oh no, you can do several steps, it's fine.
No, well, I didn't do several steps. I did like no steps. I just did it in my head. Like for multiplication of matrices, I did the
Oh yeah, that's fine.
and then.
But I doubt that you could solve like a 4x4 matrix
No, I'm just
in your head.
talking
Now,
about
I'm not saying you
for,
could. You possibly could.
I wouldn't want to, but I mean, I'm just talking about like when you
Multiply,
when you
yeah.
make it, bigger.
Please, dear
And then
God, don't
subtract
show me negative 2 times 3 plus 4 times 8. No.
Okay.
Just give me the answer.
And then also with when it's like multiplication and subtraction, is that okay just to have like one matrix and not like everything?
Do one matrix.
Well, because I did, there's like a problem where it was like, whatever it's called was multiplied by one coefficient, and then like 3a minus 2b. Like I didn't show, I just like put it in a matrix form because I did each one individually.
Sure.
And I was like,
Yeah.
okay, that times 2 is this.
Okay.
That. Okay, is that
Yeah.
okay?
That's fine.
I didn't use my calculator.
That's fine.
I don't even know how to do it.
Awesome.
Okay.
Eventually, that won't be awesome, but right now, that's fine.
Okay.
Yeah. Yeah.
I have a question from the homework. Number 46 on 10-2.
Now, real quick, last thing about this. If you were to work this out and you got a matrix like this here, say you did this problem and you got like, right? I'm trying to answer your question, Ms. Lockett.
Oh.
So you get equations like this.
Mm-hmm.
This is A, B, and C are just numbers that we don't know. So anytime I have a system of equations like this, you are completely allowed to just add those together if you wanted to. If you add these together, it's nice because then the B's go away, right?
Uh-huh.
So if your question is, I don't know if your question really is, why are you allowed to do that?
Uh-huh.
Well, because if I add 4 to this side, I have to add 4 to the other side also. But 4 is this.
Oh.
So if I add this to this side,
Sad.
if I add this to this side, then I am actually adding 4 to both sides, Your Honor. I felt like I was in a... I have John Grisham on the brain now. Not Matthew McConaughey.
I don't know if I can handle the truth, Jeff.
Is that cool?
John Grisham or the Mac?
Everything I just said. Is it cool? If you have a problem with any part of it, then it's just too bad. Because that's the way it's done. You must portray a Southern lawyer as you do this problem.
Okay.
When somebody comes to me on the test and just talk to me, I have a question, Jeff. Please proceed. All right. Any other questions from homework?
Is that the answer to my question?
I don't know. Oh, yeah. Your question was what? I forgot. Where are you at?
10.2, number 46. It's relatively easy, but I'm just wondering if I can do this right.
Oh, yeah, I like this one. 46. Pure calm. Yeah, this kicks ass. If any of you guys are doing getting into electrical engineering, possibly, or even physics, this is some of the coolest stuff to me. Because this is stuff you can really hook things up and see things happen and blow out all kinds of fuses in the process. Not saying that I do.
I did not want to learn that as a master.
This is what we're talking about, right? Hopefully. What's the trinity?
10.2.
10-2.
I mean, all the old stuff, all the recent stuff.
It's just maybe if we're like you said, if you're not going to be writing a paper, you're not going to that's really cool. Here's what's called.
All right.
Here, you just decide to.
And I don't know if anybody took the time to kind of look and compare where these things might have been coming from, but Kirchhoff says you take any closed loop, and if you multiply the voltage times the resistance and the current, they'll have to add up to the total voltage allowed on that loop. How much you have to know about that to do this problem? None of it. But it's there. And this is before we're allowed to use matrices.
Elimination.
Yeah, so you have to use elimination or substitution, whichever one makes more sense. This one's a little bit evil because you have two equations that have just two unknowns.
You just put in a 0 as a placeholder.
Well, this is
Yeah, it's not a big deal. Yeah, there's nothing there. But if you have to do this by hand, you can't use a matrix. What's your whole initial motivation? What do you want to have happen?
Set two
Keep
equations the
rid
same.
of-
Set two equations the same so we can cancel them.
Get rid of your x's.
Okay, all right, so let's kind of expand it. I want to get rid of one variable twice,
Yes.
right?
So one of
First, you
mine-
should rewrite the equations to represent, so that they're represented by x, y, and z, because that's kind of annoying.
But still, x, y, z.
Yeah, I know.
X, y, z are arbitrary variables.
Well, I sub 1, I sub 2 is just kind of annoying.
Maybe you can reduce the second one.
You can always use intermediate variable, as long as at the end you bring back I1, I2, I3.
Oh.
Because if I'm the person that gave you the problem, I better see my stuff back to me.
I did all the answers in brackets, so you wanted it
Sweet.
I.
But as you're working it out, if it changes to x, y, z, just make sure at the end it's I1, I2, I3.
You multiply the first equation by negative 16.
Well, you have to initiate what you're going to do, right?
Yeah, you could. Now, so you want to eliminate either I1 here, so that you have I2 and I3 between two of them. Or you're willing to eliminate I3, so you have I1 and I2. Is that cool?
Yeah.
So here, if you do like you said, if you multiply 1 by negative 16, and you add it to number 2, you get negative 24 I2 plus 16 I3 equals 4. And of course, the nice thing with that is
This equation
That
is
divides.
yeah, you can divide it by 4. You kind of look between these two, and you can see if I divide by negative 4, these will end up being the opposite sign. That's kind of cool. So I'll divide by negative 4. And that can bring this guy down. This is my equation 4. Normally you have to make an equation 5 also, but I already have one sitting here with one variable gone, the same variable I just killed. So I don't have to do that step. The mistake people make is they start losing spots. They do something between these two, which isn't really going to get you anywhere too quick. There is one other way to do this, which is to solve for I1 here, solve for I3 here. You get everything in terms of I2, and you can plug those two things in there. Let me say that one more time, because it is a neat way to do it sometimes. If you solve this one, for example, for I1, and solve this one for I3, you can replace I1 and I3 with those things, and they'll only have I2 in them. So this whole thing will only have I2 in it. Once you have I2, you effectively have both of the other ones. So that's a whole other way to kind of do this problem. If you have no idea what I said, you can do it this way. Yeah.
So could you think of it as just, you only have two equations, and then use that bottom one as your number 5, or as your number 4? Because you can use like the first and
Yep.
second, and then get your third, and then use that as your
I
fourth.
like it. So just use this guy
Okay.
as the one that has the same variables. Get something disgusting. Hopefully you're supposed to.
Yeah.
Oh, too bad. Yeah.
Wait, where the book teaches it is to put it in what they call triangular form, which is kind of like a precursor to matrices anyway. And then you solve for z, and then you back substitute, and
Yep.
you solve for the next variable, and then you
I like
back
it.
substitute, which is the same way you would attack a matrix. So
Exactly.
I don't. Yeah.
So they might have been trying to get us ready for doing it with the matrix.
Yeah.
But when it's like this and they have to do it by hand, there's other ways to do it besides that lockstep way. And actually, there's other ways to do matrices besides that lockstep way.
Right.
Yeah.
Yeah.
So what's more important is you understand the end goal. And the process the book shows us very often is not the only process that gets us to the end goal. So what's more important is what am I allowed to do, and what's my end goal?
But you're allowed to do that?
Allowed to do what?
To put it in a like triangular form, even though it's
Oh, hell yeah.
Okay.
Of course you're allowed to do that. Sometimes that takes longer than it should. But that would always work. Sure. Okay. Anything else? Very quick class.
Can we finish this one? Just to see.
Oh yeah. So you get 14I2 equals 4. So you get I2 is this disgusting 2/7.
See, what I did is I stuck with not dividing right before you did number 4. I didn't divide it by 4. So I kept the minus 24 plus 16 equals 4, and then I brought down the 8i plus 4i3 equals 5. Multiplied that by 3, so I can have 8 times 3 is 24.
Good.
But then my answer, I got 19 over 28.
Okay.
And that
For I3, right?
Yes.
That would get you I3.
Oh,
So let's see what we get for I3.
I got I2.
Where did I go?
Equation 3 here.
So if you do this now, 8 times I2.
Yeah, I got I2. It's 2/7. I think.
Good. Plus 4 I3. If you solve that, you should get that 19, 28. So you're in pre-calculus, so you should expect answers to sometimes not be whole numbers. Hint, hint.
Yeah.
So don't freak out if, for example, you're taking a test. You get answers like 4/5 or something. That might be okay. With me, if you get an answer like 111 out of 397, that's probably not right. I'm not going to do that to you. Let me give you guys the answer key, and then there's a few areas on the answer key that I just said in class, so we could just do it together in class. Make sure you have a front and back on this.
Oh, yes, that was the one to I'll show you exactly what that is.
Power.
Let me see if I remember.
The nth root thing was kind of bugging me on
So do take a second and make sure you have a front and a back. Yeah. So for example, 5A and B. I had forgotten that I had made these so evil last semester. I was going to change them and I did not. I gave you, on 5A and B, I gave you shifted conics instead of non-shifted conics. And the only thing with the shifted conics, you do it as if it's not been shifted, and then you just move the whole damn picture over. It's not that big of a deal. But we didn't go over it. I'm not going to do that to you on the actual test. So in the actual test, you get something like 5A would instead be something like this. What kind of shape would this be? What basic? I know that's...
It's a hyperbola.
Yeah, how do I know it's a hyperbola?
There's a minus.
There's a minus. Cool. The ellipse has a plus. So an ellipse is like a circle, but it's different coefficients, so it's differently shaped in one direction or the other. A hyperbola has got that minus in there.
And different coefficients, right?
And that doesn't matter, to be honestly. The cool thing with a hyperbola, when you draw that rectangle, remember that? you fit an ellipse in there. If they had the same coefficients, there you could fit a circle in there, but it's still the hyperbola on the outside.
Yeah.
So hyperbola didn't care what little things inside the box. But what do I have to be careful about here? First off, is it going to look like A or B here? What's it going to look like?
B. Well, it's bigger so on one side or the other.
The key here is what's positive, the x piece. So it's going to sit on the x-axis. Right. If x is 0, do I get any real answers? No, that tells you can't possibly be sitting on the y-axis, because that's defined to be x equals 0. You guys kind of with me? That's kind of nice, not too hard to forget. The positive part is the axis it sits on. Why is this not quite in the right form?
Because x squared don't have a constant. Because x squared don't have a value in the y.
It does.
Oh, 1. It's got a 1 on the bottom.
Yeah, so it's got a 1 on the bottom. What's this got on the bottom, really?
1.
Oh, I like it. 1/4. So the official form that we built all of our structures off of is x squared over a squared plus 1 minus y squared over b squared equals 1. Right? The book makes a big deal about a and b. Screw it. You don't have to do all that.
Can we write it 2? Yeah, 2 does make a big deal.
I know it does.
Can we make it
Again, I can't really blame it too much. Yeah.
Can we write y squared over 2? Like perfect square of 4? 2 squared?
That's true. 4 is 2 squared, but it's got to be on the bottom. It's got to be a denominator. So it's got to be 1/4. So then a would be 1, and b would be 1/2. Good. Because that's b squared. So, what about the asymptotes?
Oh, b over 1 over 2.
Yeah, and all this b and a crap, forget about it.
B over 1.
What's the slope? 1 over what? Rise over run, y's over x's. There you go, y's over x's. Who cares what a and b are? You guys follow? It's easier for me to say that than it is for the book to write it. So the book has to pick something, and it just makes it more confusing, but they have to. They're a book. What can they do? So here, the asymptotes would be
1/4 over
the y number over the x number. Yeah, 1/2 over 1, which is just 1/2. So it'd be plus or minus 1/2 x. If you notice the way the book did it, you can follow the a and the b around, and you can see it's the same thing. Okay, hopeful. In general, is this really... This becomes necessary just to give us a better feel for the shape. As it goes out, it should start to hug the asymptote. But what can I do even before I did that? On the x, I go out 1. On the y, I go out. That's right, 1/2. I like it. Oh, Jeff, come on. All right, your scale sucks at that matter. And of course, it sits on the x-axis because the x part was positive. So I know I can put points here and there. I can draw. I like that. I can draft. It's either draft or draw, Jack. I keep trying to make a word out of it. I can make a picture. I can make a box. Right? And you actually don't really need this step. You could just graph your asymptotes, right? Up 1/2 over 1. See how it goes right to the corner there? You guys with me? How would you graph this line? You go up 1/2 over 1. Is that all right? Rise over run. So you just go to the corners of this box because it's plus or minus. So you get these things here. And now that gives you a reference for drawing in your actual graph, following those asymptotes. Where's the focus? How do I get the focus? The foci.
C squared equals to a squared plus b squared.
Good. This one is the one with the plus because the actual equation has a minus in it. It's always the opposite there. All right, so it's the one that looks more like our Pythagorean Theorem. So c squared would be 1/4 plus 1. Z would be root 5 over 2 plus or minus. You doing okay? Yeah? No? And whatever the hell that is, roughly. It's 1 point something. 1.1 roughly. So 1.1, there's a focus, and there's a focus. So if I ask you to indicate the foci on your graph, make little open circles because they are not points on your graph. Minor point, but still.
Can we make X's? For foci? Can we make X's?
Sure, yeah. So what if the equation would have been this instead? That would be that picture moved right 2, down 3. If it's in with the letter, it's the opposite. So left 2. What did I just say?
3.
Right 2, down 3. Right 2, down 3. So this whole picture would just move over 2, 3.
Are you gonna try to open this bracket with the formula before doing anything?
Second.
You're gonna before the first step would be trying to open the x minus 2 formula, like a minus b whole square, try to simplify this denominator in order to get the equations or your foci, your vertex, and then your center.
If I was given this problem, I would do this and then shift it. That's my point. So if this was the problem, I would do all this and shift it.
Just shifting is the point. So your 4 gonna be 1/4.
Yeah, it's still going to be 1/4.
And then the x would be
Yeah, all this work would be the same. And to be completely honest, I would actually not even do that. I would first find the center. It'd be 2 over and 3 down. And then just make my box off of that center and then just throw my hyperbola in there. That's all I have to do. I first can find the center and then just build out from there. I could do exactly what we just did. Make this box, go up and down 1/2 from here, go up over 1 from there, make the box, and I can do the hyperbola off the ends of that box. If I just first find the center, I can do everything we just did. Either way, you can either do everything there and then shift, or you can shift, which is the way I normally do it, and then just build off of that. So it's not too big of a step. The problem is, of course, it would normally not start like that. It would normally start like what I have on the test, which would involve completing the square.
That's why I asked you.
Oh, yeah.
Can you again say why b is 1/2?
Because it's b squared.
Oh, yeah, so remember this is x squared over a squared,
Yeah.
y squared over b squared. So b squared is 1/4, b must be 1/2, the square root of that.
Okay, so
Yep.
1.
And it would open upward if y were bigger.
Yeah, these were, if y was positive and x was negative, it would open up and down. Yeah.
How to find the circle one more time? Is it an equation for that?
The circle?
In the practice test it says find the circle, vertex, foci.
The center?
Yes, center, sorry.
Center. Center would just be 2, -3. 2, -3. Yeah. Because that's how it's been shifted. Whereas the center normally at 0, 0. If every point shifts over 2, down 3, then the center shifts over 2, down 3.
Oh, it's y minus y.
Maybe, maybe. Let me see. Can you tell what kind of shape 5b will be?
That'll be y squared plus x squared. That's an ellipse.
Yeah, exactly.
Except for there's something going on there, like moves or Something weird going on there.
Yeah, definitely. Some freakiness.
Would you put something like that on the test?
I could say identify this shape. And all I have to do is this to identify it, really.
Yeah.
Because I know it's got x pieces, x squares, and y squared piece. So I know it's going to have to be, and it's plus, these are both positive. They don't have the same coefficients, though, so it has to be
What's an ellipse?
Grouping. Trying to take the x out.
No, what shape does it have to be?
Well, it's got to be an ellipse.
An ellipse. It's got to be an ellipse.
X squared.
If this would have been 9 also, it would be circle. Because they're both the same coefficients, it would be a circle, because then it would be the same in both directions.
Right.
So to do this, I actually would have to keep the square, yeah.
But you
Real
wouldn't
quick.
have this part on the test, right?
Why not? Completing the square is very useful. And if you go to the next level not knowing how to complete the square, I will cry all day and night if your teacher tells me. How do you get the number here to complete the square?
Half and then squared.
Yeah, half of -6. -3 squared is 9. And I know it's going to be x minus 3. So immediately I just did what? I just added 9.
Add 9
Better add 9 there. What goes here?
Squared.
Half of 2 is 1. 1 squared is 1. So I know this is going to be y squared plus, no, yeah, y plus 1 squared.
You have to add 9.
Right, because half of 2 is 1, half of 6, -6 is -3. That's how it factors. It's nice. But what did I just do here?
Added 9.
I added a 9, so I better add a 9 to the other side also.
Y plus 1 squared equals
And then 2 reasons why this is not quite in the right form yet.
4, because there's no 1 on that side.
There's no 1 on that side.
And there's like a...
I like the way you said it. There's no 1 on this side. And also, what's in the wrong place? The 9's in the wrong place. So if I divide by 4, to bring the 9 down, divide by 4, bring the 9 down, there it is. Where do I get 2 from? That's neat. 1. So what's the center of this ellipse?
-3 plus 1.
3, -1. Shifts are always the opposite of this. All the inputs have to be 3 bigger than they were before, so now it goes over 3, yeah. And how far in the x direction are you going to go? 2. And how far in the y direction are you going to go? 2/3. I love it. See, ellipses are nice. Ellipses kick ass. Because once you go 2 and 2/3, you make your little stewy head, and you're done. So you're fan with that one, yourself. Or football.
We call it
Whatever.
Or hey
Huh? What is it?
Hey
Hey
Arnold.
Arnold.
Oh, hey Arnold. Yeah.
So why is there 2 plus 9s?
1 plus 9 for there, and 1 plus 9
Oh,
for there. Yeah.
Equal...
And it's nice because I couldn't handle a negative number over there. It freaked me out.
Why is it 4 over 9 and not 5 over 4?
It was 1/9 times 4.
Because if I bring the 9 down,
Because you want to go the same coefficient, right?
what would that look like? Bring this 9 down.
Well, it started out as
What would it look like down here?
1/9.
1/9. Right? Because
Why is it 1/9?
multiplication by 9 is the same thing as division by 1/9. Because you do the reciprocal, right? Y plus 1 squared divided by 1/9 is the same thing as y plus 1 squared times 9. Right? That needs to become second nature. That needs to be no freakier than 2 plus 2 is 4. Taking a whole number up here, making a fraction down there, no freakier than that. It should make complete sense.
Is it like the twice thing, where it's like counterintuitive, where twice x of y instead of like...
And smushes it instead?
Well, instead of...
Sort of, because when you divide by a
2y.
number less than 1, your thing becomes larger.
No, I'm talking about the 2x equals y. You're saying twice x is y is actually 2x
40 over 9.
What's 2 square roots?
No. No. I'm just going to say no. I'm not sure what you're saying.
Plus or minus.
Now, the other thing is I have to divide by 4. So if I divide by 4, is multiplication by 1/4, so the 4 just comes up here. 1/9 times 4 is 4/9.
2.1. So there's 2 of them. There's only one's here.
If you want to do it more directly, you can do this. 9/4 multiply that by 9/4 is the same as dividing that by 4/9. Multiplying this by 9/4 is the same as dividing it by 4/9 because you have to reciprocate when you go from one to the other operation, right? There you go. Yeah.
2.6.
It could be. I wouldn't make you graph it, but I would make you talk about it. Yeah.
So completing the square.
I'm starting to be more and more definite. I'm going to put one on there.
Completing the square first.
Yeah.
First step. And then you have to set this equals to 1 no matter what. Like
Yeah, the form of
it has to be zero.
everything we built the structures off of required to equal 1.
In only negatives or in
So, I mean, we see that a few times. What if I want to use synthetic division? What kind of thing has to be down here? Or at least, give me an example. Can I do this with synthetic division directly?
no.
No, I have to do by I negative by that stuff.
So it's
I have to have a linear thing. Why must I have that there? Because that's what it was built off of. So we have these processes in place. I can identify the parts, but put everything in the right place. Just like y equals mx plus b. I don't even know if students realize it should be kind of amazing that you just solve for y and everything falls into place. But of course it does. They fall into their definitions. So here, it's required to equal 1 in order for me to see all the parts. Yeah.
But
Yeah. Oh.
even once again, they're only in the eclipse or in other 2 shapes too?
Yeah, for a hyperbola, for an ellipse, for a circle, it didn't have to equal 1 because a circle is nice because, again, it's got the same coefficients. So, I mean, we could have built the structures off of it equaling anything, but that would have looked disgusting. Circles can handle it because they're a little more direct. Whatever number that is, it's the square of the radius. Circles don't care. They're a little more laid back. Right? Any way you go, it's the same. Yeah.
Circle is circle.
Yeah.
Yeah, I was just going to ask if you would get an incorrect answer, and instead of dividing by 4, if you were to subtract 3 from both sides. I know it would get really messy and confusing, but would that still work?
No, it wouldn't. No.
Why not?
Because the form does not allow for a stray constant here. Right? It's sort of like saying y equals mx plus b plus 1. Can I just put I don't want to put that together with the b because the b is 7/9 and I don't like fractions. I don't care. You got to. Does that make sense?
Yeah.
So then the first one.
Yeah.
Can you explain why Sine ellipses are is equal to a squared minus b squared, and why it's a squared plus b squared?
We did go through the derivation, right, of ellipses, where they come from. That disgusting.
Oh yeah, we did.
Yeah, we don't want to do that again. Don't go
And it is purely because, and I really want you to make. It's almost unfortunate that they chose the letters they did, but they just chose the first 3 letters of the alphabet. So what can you do?
Yeah.
But it ends up hyperbolas. It looks like Pythagorean Theorem, and ellipses it doesn't.
Yeah.
And it's just too bad. When you derive an ellipse, you get to the point where you have a squared minus b squared, in a couple different places. I don't know if you guys remember. So we just decided to call that c squared.
Okay.
If you do it with we didn't do the whole hyperbola derivation, but it would have been like this, and we would have just called that c squared. So it's not Pythagorean theorem directly,
Not really.
but it's just a substitution step.
So just remember it.
Yeah, just remember. Yeah, the short story. Just remember.
Can you do the 12 one here?
Sure.
To understand the more, you have to understand
Oh yeah. Mwah.
more. I don't know.
Did you teach this do more?
I did.
Okay.
But to know that, you have to also understand where z equals r cosine theta I sine theta comes from.
demoivre is
Pounds and pounds.
this here.
Comments everywhere.
First off, if you have, part of it is if you have a complex number, you can write it like this. Question, remember that?
Yeah.
Section 8283, somewhere on there. And then de Moivre's theorem is actually, if you take this complex number to some power, the beautiful thing it does here is it takes the r to the power, which makes sense. But the really nice thing is, it ends up just multiplying the angle by, and we actually derived why that was. It just uses the addition and subtraction formulas for sine and cosine. If you don't believe me, there it's in the book. Yeah.
In calculus, as far as all the addition and subtraction, all the magic formulas we do, please. Are we going to be going over that again, or are you going to walk in being expected to be like?
No, I do, when I teach calc, I'm teaching calc in the fall, I do a very, very quick review of trig. I'm talking quick. And I just say, you should all know this coming in. And I give out, I think I'm probably going to give out the same sheet. I'm going to say the same thing. You need to know all these, and these other ones you don't necessarily need to know, but you need to know where to find them. Because you're in the middle of a problem doing something, and this is not anywhere near as, you're not an ER person needing to know your problem, but you're in the middle of a math problem, and you just need to really quickly rewrite something so you need to know those. So very quick review, but more of a you need to know this, and if you don't, you need to go somewhere and get a review, a more extensive review than I'm going to give in the class. Yeah.
But that's what we did in this class for algebra or 110, right? In the beginning we did a little bit.
But if we're sitting here,
and I'm one of the few that actually does that.
If we're sitting
most of my colleagues don't
today,
do that very first chapter.
We should know that.
Yeah.
Can you give an example, like try to solve a question from this de Moivre's?
Yeah, so that's the one we're going to do right now. I was just reminding you what it was, because that's a good question. What the hell is that? So now, if I could rewrite this, what was it?
12.
Where'd it go?
12.
Thank you. 3i minus 3. If I could rewrite this part, that's my complex number in that form. So now you got to remember how to do that.
Oh yeah.
So it's nowhere near as bad as it seems. The main thing to remember that will make it easier to memorize this is that if you were to graph this, and I know I don't ask you to do this, but if you were to graph this, where were the -3 and where were the 3? Which direction?
Well, it's 3 pi. It's like 3 pi.
Which axis is this? The real or the imaginary?
That's real.
Good, that's real.
So you go to,
it's the imaginary.
You go to,
so which real or imaginary? Which one acts like x?
-3.
Yeah, the real.
-3.
Right, so it's the -3, 3. So there it would be, right? So really, changing that form, I'm just asking you, what is that r? Okay, that's Pythagorean Theorem. X squared plus y squared equals r squared. Real is x. Imaginary coefficient is y. And then how do you find this angle here? Actually, it would be this angle that is
Tangent of y.
Yeah, so you have x squared plus y squared
well, it's 3, 3.
is r squared, which translates into a squared plus b squared equals r squared because it's a plus bi, but who cares? And then tangent theta must be y over x. So b over a, y over x, imaginary over real. So if you just remember this, this is the same stuff we did before. Didn't we do tangent theta equals y over x? And the y is the imaginary. Okay, cool. And the x is the real. So this would be tangent theta equals 3 over -3, so equals -1. So what's theta equal then? When is tangent negative? When is tangent -1?
3/4.
Some pi over 4 reference angle. What quadrant do I have to be in?
2 or 4.
But in this case, I have to be
2.
2 because I know this is in the second quadrant, right?
Yeah.
So that should
So I
make
want
sense.
this to be pi over 4.
Yeah.
So then what's my angle? 3 pi over 4. Cool. And what's my radius? 3 squared plus 3 squared.
Square root of 18.
Square root of 18, square root?
3 root 2.
3 root 2. Hold on. Are you guys with me so far? And that actually is the work you would do directly on, where'd it go? Oh, here we go, number 11.
So
Number 11 would be exactly this work here.
Oh, that was number 11. So that's calling for finding r and finding the angle?
3 root 2, and then the cosine of the angle, which is root 2.
So now, I've gotten this rewritten in this form. So I've got 3i minus 3 equals 3 root 2 cosine of 3 pi over 4
I sine 3 pi over 4.
plus I sine of 3 pi.
Which we know.
Yeah.
You good so far? And if you did the work, this is where it's almost silly. If you did 3 root 2 times it, what is cosine of 3 pi over 4?
Root 2 over 2.
Negative root 2 over 2. And what's 3 root 2 times negative root 2 over 2?
6. Negative 3.
Root 2 times root 2 is
2.
2 divided by 2 is 1. Negative 1 times 3 is negative 3. And isn't that the real part there?
Huh.
This is the real part, and this is the imaginary part. I mean, if you work it out, you get those numbers. So on one level, it's like, duh. I'm not saying duh for you, I'm just saying for the whole process. Duh. If you work this out, you get the real part. If you work this out, you get the imaginary part. But it does take a little bit to work out what angle would make that work for both pieces.
Then you
Right?
have to times it by 5.
Yes, ma'am.
Oh, you have to do
Oh, sorry. Just this here. So it'll be negative 3 squared plus 3 squared. R is the square root of 18.
And you have to do this.
And then simplify that.
And that's the most there. That's good.
So,
This times
yes, sir.
I want to ask again.
Oh, we're finally able to do the actual problem. Raise both sides to the 5th power. So that will equal this to the 5th power.
Yep.
Which, if I remember correctly, was 972. Is it? Well, I did the answer key, so what the hell? I can't see it. It's on the answer key, so I don't
It's 972.
972. Cosine of what? What happens to the angle?
2 times 3 is 3 pi by 5. Well, 3 root 2 to the
Oh, 972 at the very end. Sorry. So what's 3 root 2 to the 5th?
is
Oh, it's going to be something ugly.
137.6.
So I'd rather do this. I'd rather do 243 times 2, so I can get you guys more. Square root of 2. I think I did this on the answer key.
Yes.
240. Oh, okay.
Yes, you did.
Because then it's easier, because we're going to get some root 2's out of the inside, so I might as well leave that as root 2. If you multiply it out, you actually get some decimal. What happens to this angle by raising to the 5th power? It gets multiplied by 5.
Yeah, times.
So it's 3 pi over 4 now, so it's now
Plus a 15 pi over
15
4.
pi over 4 there.
Plus I sine.
15 pi over 4
15 pi over 4.
there. And the last step is just work it out and see what it is. So if you think about it, we took this problem, put it in a different form where the work is easier to do, and now we're going to take it back into this form. And it's a hell of a lot quicker than writing this out 5 times and foiling that many. Screw that. So you actually, if you take a minute and you work this out, remember, this is very useful. What's the cosine of 45 degrees? Cosine of pi over 4? Root 2 over 2. Remember, that's actually 1 over root 2 rationalized. So this would be a good place for that to happen, right? Because when your root 2's would cancel. Unless you don't like that at all, it doesn't matter. We all have calculators with that. So you get 243 root 2 to the 5th times the cosine. Where's 15 pi over 4? Where would I be?
4 pi.
Yeah, it's almost 4 pi, which would be all the way back here, so it's there. So cosine's going to be positive or negative? Positive.
I root 2 over 2.
And sine is going to be negative. Kind of the other way. So now you just got to multiply that out.
Oh, 972 root 2 is what?
And that's where you get the 972 final.
Some math questions. If the 243 times square root of 2 to the 5th, does the 5th power go to 243 or just to the square root of 2?
it goes to both of these, right? So 3 to the 5th, root 2 to the 5th. I did 3 to the 5th. I didn't do root 2 to the 5th yet.
And then over here you have 15 pi over 4 to the 5th. Or
No.
3 pi over 4 to the 5th is...
15 pi over 4.
No, it's this thing to the 5th power. I'm not taking this to the 5th power at any time.
Okay, so how'd you get 15 pi over 4?
Because that's the rule, and the rule was proven in class a while back.
Oh, yeah.
And it's in the book too, if you forgot. That's an easy one to forget. It's on page 559.
Times the top of it.
What was over 1? Page 359.
559, sorry.
So according to the given problem, 3I minus 3 to the whole power of 5. So if the question says negative, we're gonna use the positive formula.
What?
So if the question says negative, we're gonna use the positive formula like r and cosine and theta plus imaginary sine theta.
That's the one we use.
Yes, sir. But like if the sine is negative, we're gonna use the positive. If the sine is positive, we're gonna use the negative. When do we, the main point, when do we know like which formula are we going to use?
There's only one. I don't know. So if you're talking about the difference between this one and finding the roots.
Yes, sir.
So the roots is its own thing, right? And it's based off of this. So if I wanted the nth root of some complex number, that would be the nth root of r. And what do you think happens inside here? Yeah, it's basically theta over n, but then you have to include all those other possibilities, right? Plus I
You have to
sine, the
add
same thing.
k pi to each of them. You have to do them one at a
Where
time.
k goes from 0 up to n minus 1.
Yeah. I think you have to do them one at a time.
And I don't know if you guys remember, but I showed you why that made sense. When you divide, you actually kind of make more room for more things to fit in between 0 and 2 pi. It's kind of nifty. It really is kind of nifty. Just didn't have enough time to really get into it more deep. I'm probably not going to give you a problem with this.
Oh, thank God.
All right.
I know. Just,
There you go.
if I do, I'll give it to you in the bonus. So if you're able to do this kind of thing, look for the bonus. It's not that big of a deal, though. Just takes getting used to, like anything. We didn't have enough time to really get used to it. What else do I have on there that I said I'd work out? Oh, sorry.
Oh, boy.
Okay. On 9A, I was all good up till getting the r squared equals secant 2 theta. But then from that, how would you graph that? Like, how would you find the...
Oh, yeah. So that's the other thing I have to do. So on number 9A, so it starts off here. If I have to change this from rectangular form to polar form, what's my conversions that I use?
R sine.
Yeah, x is r cosine theta, and y is
Our sine.
r sine theta. So I just collect those r's there. And in general, it's the same thing as trying to get a function or solve. I'm trying to solve for r, so I went as far as this. Wait, before I go too far. What is 2 sine theta cosine theta? Sine 2 theta, 11. So then if I divide by sine 2 theta, I get 1 over sine 2 theta. 1 over sine is cosecant. So I get that. If I go one step further, I get this ugly beast. Oh yeah. So to graph this truly, if I wanted to graph it from the polar form, I would have to graph, the positive ones and the negative ones. So I'd make my table values like always. Start plugging stuff in, right?
Yeah.
Yeah.
So you'll be giving us a polar piece
Yes,
of paper
I'll
to
give you
graph.
some polar graph. I won't give you one quite as ugly as this.
Okay, thank you.
I mean, that one I shouldn't even have said graph. Because number 10 is a little closer to what I give you. And to tell you honestly, I did the work for converting over to, and you can see how ugly it looks in rectangular form. I mean, really ugly. But if you wanted to graph this one the way it is, in polar, you can just directly start plugging stuff in. Right. Plug a 0 in. What do you get? Sine of 0 is 0. You get 0. Plug in, now I can be smart about it, plug in pi over 12. Because I'll end up with pi over 6 exactly. And that polar graph paper that I gave you has it in terms of pi over 12. That's actually the smartest choice because it captures all your pi over 6, pi over 4, pi over 3. It catches all those.
Will you be giving us that with the pi over 12, blah, blah, blah?
Oh, yeah. So here I'll end up with sine of pi over 6, which is 1/2, good, because it's closer to x. Sine doesn't like x, so it's going to be small. And twice 1/2 is 1. And you just keep going. Then you do pi over 8, because you'll get pi over 4 coming out. But pi over 8's not on there, so who cares? So just think about cutting in half what you normally would plug in, just so you get that actually showing up inside your sine.
Because you did not consider squared, right?
Double, yeah.
Because of the 2 theta.
Now, if you wanted to, what is sine of 2 theta?
Cosine squared theta.
Careful.
Careful.
Yeah.
2
sine theta, cosine theta.
Cosine theta.
So this would be 4 sine theta, cosine theta. You could certainly do that instead of doing this. So you'd have your 0, your pi over 6. So look here. What do you get when you plug a pi over 6 in there? Twice pi over 6 is pi over 3. What's sine of pi over 3? Root 3 over 2 times 2 is root 3. Now what do you get when you plug a pi over 6 in there? You get 4 times sine of pi over 6 is root 3 over 2. Cosine of pi over 6? 1/2. The 2's cancel the 4, you get root 3, the same damn thing. So it doesn't matter because that is that. You used identities. Whichever way you like better, I don't care. You actually get a little more resolution on this one, if you think about it, because you're able to handle those uglier angles. But that would work just as well. Apply an identity and make your problem, if it's easier, make it easier. I don't know if it's easier or not.
Does it matter if you start from 12? I mean, pi over 12?
Whenever you have this double, you should try to recapture what you normally would get when you put it in there, yeah. That's the one problem I have with this. And again, I don't know if you all get this. You might not get enough resolution here because you're actually jumping over some stuff. You might not know how far it goes out. You might miss something if you don't get enough resolution. If I didn't graph enough points, I wouldn't know. If it's supposed to go like this, and I don't graph enough points, I might think it goes like that, and you just kind of skip this whole thing. Does that make sense? So maybe not that extreme, but you might get something like that if you're not careful. So something with twice an angle, and it should not be that big of a deal when you graph it. Just cut in half what you normally would plug in there, and you get those things coming out. Maybe. Yes, sir.
553, sir, question number 9, 8.3. That's question number 30. 553.
Number 30?
13. Question number 13.
Oh, 13. Okay. Oh, yeah. So this is the...
Symmetry.
Yeah, exactly. So every now and again, I actually purposely skip over some things. Just to see, and I don't think anybody asked about this, but I just took that to mean everybody understood it in their own. So test for symmetry in polar coordinates. So we know how to test for symmetry in rectangular coordinates when you put f of x and f of negative x and you compare, see if it's even or odd. We at least have those two. Here we have more. If we replace theta, if it's unchanged, if f of theta is the same as negative f of theta, then it's going to be symmetric about the polar axis. And what they really mean, thankfully they have on the bottom of page 550. They have exactly what this means. And the funny thing is, you'll notice the polar axis, another name for the polar axis. So if you had this theta versus negative theta, and your output's the same. So what kind of shape would you use, no matter where you are? So this theta and this theta have to have the same output, so forth. So they actually have to be symmetric to, it's a better way to say that then. It's got to be here and it's here. To the y-axis, yeah. I like it. So this is really another name for y-axis symmetry. But we're in polar coordinates, so we can't refer to it as a y-axis. So it's kind of like the origin for the pole, for the origin for r. That's another way to say it. The origin for angles, because they start at 0 here and they go from there. So we call that the polar axis. It kind of goes from there. So that's one type of symmetry. So all you got to do is plug in negative theta and see what happens. If it stays the same, then it's got polar axis symmetry, basically y-axis symmetry.
Meaning it'll be the same on either side.
Yeah, it'll be the same on either side of y-axis. Exactly. So if it looks like this up top, it's got to look like, oh boy, that down below. It's not too bad, considering we did it. If we replace r by negative r and it stays the same, in the picture they show here, this sounds more like
And this would be on the test, but it's just a question.
nah, it's just there.
I'm thinking of it as like,
So the example they give is something like this here. Origin symmetry, you guys remember that? It's also known as like odd symmetry in rectangular coordinates. It's through the origin, it's symmetric. And then finally they have, if you replace theta by pi minus theta, that's y-axis symmetry. Here's theta. And this one here is pi minus theta. Not here. Here's pi, so pi minus theta would be all the way out to here. Here's theta. So pi minus theta would get you here. So if you're symmetric like this, if you replace theta by pi minus theta and it stays the same, then that's the kind of symmetry you have. You have what I would call y-axis symmetry in rectangular coordinates. Yeah.
What are the differences between the first example and the third one?
Here replacing theta by negative theta.
If they're both y-axis symmetry.
No, this is x-axis symmetry,
Oh, it's x-axis.
and this is y-axis. Yeah, see?
Right. It looks like a line.
Yeah, but this is not the same on the other side.
Oh,
This is the same on the other side, like that.
She
Yeah.
means the y that you wrote.
Yeah, you wrote line.
Oh, it did come out like that. Sorry. Thank you.
But it's actually polar axis.
Exactly. Yeah, I would never say this when I'm talking about polar coordinates, because then in terms of polar coordinates, what the hell's x?
So then, I meant, like, on the third one, you have two polar coordinates. What is that one?
Oh, I don't know if it has a name officially.
Well, like,
No.
what is it in terms of a polar coordinate, rather? Like,
This, what do you think this line is here? What's the equation of the y-axis in polar coordinates? What's true at the y-axis? What's true at theta? Theta, and that's exactly the equation. So this would officially be called symmetry about the theta equals pi over 2 line. Which you'd hope somebody would sit down and work on a name for that. That'd be great. Maybe I will.
So it's like symmetry about the angle.
Symmetry about this line, which we would call the y-axis in xy coordinates. But in terms of polar coordinates, the best we can do is say it's the theta equals pi over 2 line. If theta is pi over 2 and r can be anything, you end up with the y-axis.
Oh, okay.
Yeah. If I face this direction, r can be any positive or negative number, I end up with the y-axis.
So, sorry, because I just considered not half of the angle, but at the coordinate of pi over 2.
Yeah, exactly.
Okay.
At the theta equals pi over 2. Yeah.
Okay.
Cool. Anyway, so if you have problems like that in the homework, all you have to do is replace the theta by negative theta to check this. R by negative r to check this. And anything, obviously, like the one we did, r squared equals cosecant 2 theta, that's obviously going to have this kind of symmetry, because r squared is going to eat up the negative when I throw it in. It's going to stay the same. And then replace theta by pi minus theta to see if it has this kind of symmetry. I can't remember if I just assigned too many problems like that. I just wanted you guys to realize that the idea of symmetry is still there, even if I change coordinate systems. There's always some kind of symmetries to be talked about.
This question wasn't much, like you just have to tell which symmetry this belongs to.
Yeah, you just have to do what the tests ask you to do. Replace theta with negative theta, so forth.
And then r with minus r.
Exactly. Just to check each one of the symmetries. Yeah. Oh. So, if I give you the point 3 pi over 3. So I kind of gave a crappy little graph, but pi over 3 is there. So 1, 2, 3. Here's 3 pi over 3, right? And I ask you for 2 other representations, one with positive r and one with negative r. So you already have one with positive r, but I need another one, and then I need something with negative. So what's another way? Really, then I just have to figure out another way to reference this angle. And I could do like negative, or I could add 2 pi on top of it. I can't remember which way I went on the answer. Pi over 3, what would that be as a negative angle to get to the same location?
Negative 5 pi over 3.
Yeah, negative 5 pi over 3, good. So that you're pi over 3 short of making complete backwards turn. And then negative 3, I'd actually have to end up here, wouldn't I, and then go back 3? So what angle would this be? How much past pi is it? Pi over 3 past pi. So what's pi over 3 past pi?
4 pi over 3.
Yes, 4 pi over 3. There's another way to write that. Or you could call it negative 2 pi over that. I don't care, as long as you end up there. So if your r is negative, you actually have to think about, actually have to look this way and move backwards. So then you got to work with this angle to get that to work. So that's the weird thing about polar coordinates. Because it turns on itself, there's an infinite number of ways of identifying any given point. That's really showcased in the sine and cosine repeating itself forever. All right. Yeah. Go ahead.
When converting rectangular to polar, to then find the graph of that, I know you don't ask for that on the practice test, but to find the graph of that, like when you get tangent theta equals negative 4 over 3, would you just take inverse tangent to find theta so that you could graph the...
Yep, exactly. Yeah, so if you get, if I said graph this, you want to figure out what theta is, and it would basically be the line that's, just like the theta equals pi over 2 is the whole y-axis. Whatever angle this is, so negative 4 over 3 would be here, so it would be like that line there. What did I just do? Yeah, I got it right. Just did an interesting way to do it. Negative 4 over 3. What y there? Is y over x.
Yeah.
That would be about right here. whatever angle that is. So you can do the inverse tangent, and you can be in degree mode, so it's a little bit better feel for what the hell's going on. It's kind of cool. So when r is missing, r can be any value, so you get all values of r. So it must go forever in both directions when r is missing. When theta is missing, it has to go forever all the way around. So that's why the equation of a circle is like r equals 2. Doesn't matter what theta is, so it goes through all the values of theta. It's kind of neat. Of course, same thing happens in rectangular. X equals 7. What's that going to look like? Yeah, straight it down. It's going to go through all the values of y because y is missing. There's no restriction on y. Y must then, can then, and will then be everything. Cool. That carries through all the different coordinate systems. Yes, ma'am. Yes, I love it, because that's not a value that we know. That's for damn sure. I think it's down to be 53 degrees. Maybe. Yes, finally, sorry. Yeah, 13 and 14 I said I would do up on the board. So let's go ahead and do both 13 and 14. Yeah. Uh, 13, evaluate using the half angle formula. Of course, 5 or 12 is what cut in half? 5 or 6?
You gotta write some of your outlines.
What's the half angle formula for sine?
You do your homework chemistry too.
It's not one that I said you had to memorize, but
See, half angle is
yeah, plus or minus. Chris.
get rid of 1 minus cosine.
Yeah, but cosine is plus. If it's not, cosine is minus. Remember, cosine, I don't know if it still works here. Cosine doesn't, it still works here. It's the jackass. It says, oh, your sine, if it's cosine here, it'd be positive. So, he likes himself. Exactly. So you get. So I think what really trips you guys up is you don't really identify for yourself what the hell theta is. If you write it like that, theta is pi over 6. So theta is pi over 6. What you all you end up doing is putting an angle here you still can't do. Well, what use is it then? And you're probably thinking the same thing. What use was that? Let's go to the next one. So I've got to end up with something here I can actually handle. And in this case, it's going to be plus or minus. Positive because I'm in the first quadrant, right?
Yeah.
So that's part of the problem too. Don't leave that there. You've got to actually take a second and think, where am I? So 1 minus cosine pi over 6. What's cosine of pi over 6?
Root 3 over 2.
Yeah, root 3 over 2. And here's where we have some trouble too. I like it when those 2's just cancel or something. Right? So be careful. The smart way to do this to kind of keep it straight is to multiply top and bottom by 2. So you get 2 minus root 3 over 4. Of course, the square root of 4 is 2. You get these embedded roots. Right? Now the funky thing is, you could do the same thing possibly using sum or addition subtraction formulas, and you end up with a rather different looking answer. But it's actually kind of a rationalized form. So if you guys look back at your quiz, if anybody did, sine of 3 pi over 4 plus whatever, you did like a addition subtraction formula, you ended up with something that looked more like square root of 6 plus square root of 4 over 2 or something. Over 4, whatever it was, yeah. Yes. Something, yes. That and that are actually the same thing if that's equivalent. It's really not this and this exactly, but if you were to do the same problem using this processing into something that looks like this, they are actually the same thing. It's kind of freaky.
So we won't be wrong if we do this time.
You will be if I say use the, like I did here. Part B, same idea. I'm not going to probably do this the whole way. Let's double that. 330, and that's an angle whose reference angle I know. The value's 4, right? So cosine 330 over 2, and this is what we were just talking about. It's going to be positive or negative?
That's positive. Positive.
Which quadrant am I in?
4.
I'm in second quadrant. Now look at 330. That's not the angle that I'm evaluating. I'm evaluating 165. I'm doing it in a way that allows me to use an angle I know, but it's still at the heart of it. The problem is all about the angle 165. I'm in the second quadrant, so cosine is negative. Don't look at 330. 330 is what we're doing in the middle to make it easier. The problem wants 165. We, of course, say, screw you. Let's use an easier angle a different way. So this is negative 1 plus, because he likes himself. So does that person. And now this is where I was talking earlier about some of you guys brought the reference angle in too early. In this case, it's not going to matter, but if this was a sine and you put a 30 instead of 330, that would change the SIGN of it, right? The sine of it. Cosine of 330 is going to be positive anyway, right? Because I'm in quadrant 4. So if you make a mistake and you put a 30 there, it's going to be the same answer, but you got to be careful. It's not right. That's a 330. You use the reference angle there to figure out what that is. And what's the cosine of 30? No, 30 is pi over 6. What's the cosine of?
1 square 3 over 2.
Yeah. Root 3. And now you do the same kind of, it's the same thing as this, except with a plus in there.
So
yeah, all right.
can you do the math real quick on that? Because I'm getting the 2 out of there or whatever.
So then multiply top and bottom by 2. And then taking the square root of the bottom.
Oh.
How did you get 330 again? Is
Double
it the
this.
whole pi? Oh no.
Double that, yeah. If I have to use a half angle formula, this must be half of an angle I know, so just double it to see what it is. All right, so number 14. Is these 3 equations. What do you do here on 14a? Just remind you guys, this is not on your answer key, by the way, so you might want to write this down. I don't want to divide by sign, because if I do that, I lose answers.
This is a formula for
2 times 1 minus.
And then factor, yeah. So you get sine theta,
sine theta minus sine theta.
2 sine theta minus 1. So you get either sine theta is
0.
So you could divide by sine as long as right when you do it, you write this down and solve it, because that's the answer you would lose. Divided by sine loses that answer. Poor little dude. But here you can see that coming out. Sine theta equals 0, or sine theta equals
1 minus 1 over 2. 4 plus 1 over 1.
1/2.
This is chapter 7.
This is the last part of 7, yeah, that's where they did trig equations.
This is not 2. That's it. That's where we just go.
So then what do you get here?
Did you bring her present?
Theta equals 0.
0 or
Theta equals
2 pi is really the same thing.
Pi.
Pi. Good, that's the important thing. And so what can I do there? I can bounce between the two of them, right? Yeah, so theta equals 0 plus pi k, so I just end up with pi k. I don't want to do 2 pi k because then I skip over that second answer. Yeah.
But in tangent, you only do pi.
Depends. Yeah, normally yes. And then sine theta equals 1/2. What's the angle got to be for that?
Pi over 3.
5 or 6.
6.
Sine doesn't like x, so the closer I get to x, the smaller it gets until it just disappears in a fright. It starts coming back. 5 or 6 or?
5 pi over 6.
or
You're not there.
Second quarter.
yeah.
So it's got to be in the upper hemisphere, right? So either pi over 6 or 5 pi over 6.
Pi over 6.
Cool. So theta equals pi over 6 plus
2 pi k.
2 pi k, because I can't possibly capture them both. It takes different steps, different step lengths between both. So the whole answer is this.
When you're doing the 2 pi things, it has to actually like land on the answer, like when you go around 2 pi.
The beautiful thing about 2 pi k is it forces it to always land back on that answer you know is true. So don't make a big deal out of that. You can always do plus 2 pi k for any answer you get. Plus 2 pi k must also work. But
When you have to put 2 answers and when you don't.
so for this answer, if I rotate all the way around, I get another answer. I'm guaranteed to, right? Because the period of sine is 2 pi, so it's going to go back there. I can't possibly pick that answer up by a single definition of a step, because if I define the step to be this big, I'm going to pick up answers that I shouldn't pick up. There's no way to write this by saying every other time